Hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 6. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. We are going to continue our discussion on the topic of carrier transport in this lecture. Okay. So, let us start. In the previous lecture, we discussed the topic of drift current density. Okay. What is drift current? Whenever there is an electric field present inside a semiconductor, charge carriers are going to drift, okay. Electrons opposite to electric field and holes in the direction of electric field, and that produces the drift current inside any semiconducting material. Okay. And the equation for drift current, for electrons as well as for holes was given by this. Okay. I should just write it a little bit here. So, the drift current, total drift current okay, electrons as well as holes. This is what we had derived in the previous lecture. Today, first of all, I want to start or do a small discussion on the topic of carrier mobility. If you see this parameter here, there is some kind of a similarity both for electrons as well as holes. Obviously, they depend on the applied electric field, but the value of current density is actually controlled by the material properties. This is the conductivity. Okay. N q mu n is the electron conductivity, p q mu p is the hole conductivity. Okay. So, it depends upon carrier concentration, charge as well as the mobility. Concentration you can control via doping. Okay. So, once you have done the doping, you basically have not much control on N and P, the carrier concentration. Okay. Another parameter or material parameter which affects this current density inside the semiconductor is the carrier mobility. Okay. Under the influence of electric field, charge carriers drift. Okay. At low electric field, we have said before that the drift velocity is proportional to the applied electric field, and this proportionality constant is nothing but mobility with these units, centimeter square per volt per second. This is the units of carrier mobility. Okay. How it is defined? It is the ease with which charge carriers move inside a crystal, and mathematically it is dependent upon relaxation time, the time between successive collision and the carrier effective mass. Okay. This is carrier mobility. Now, the movement of charge carriers, whether it is electrons or holes, it is not that straightforward. Okay. Even if you have applied an external electric field, these charge carriers are going to undergo certain collisions, okay. And this is going to affect the path, the pace with which they move inside the crystal, which basically means that the mobility is affected by these collisions. Effectively, you can say that the mobility is different from the expected value and is influenced by the scattering of charge carriers. Okay. So, an electron which is moving in this direction, it might change its path here, it might collide with an ion, it might collide with another defect, it might change its path, eventually it reaches its objective. Okay. So, this is the kind of a path which charge carriers can take up. So, you can say that there is continuous scattering, but the overall direction is same. Electrons move from negative to positive and holes move from positive to negative. There are broadly two scattering mechanisms that dominate inside a semiconductor, and these affect your carrier mobility. These mechanisms are known as phonon or lattice scattering. Okay. Either you can use the word phonon scattering or you can use the word lattice scattering. Another mechanism is known as ionized impurity scattering. Okay. So, we are going to just quickly study these two scattering phenomena. Phonon basically means an atom which is vibrating about its own place. When you apply external energy, that energy gets dissipated at different places, okay, via energy conservation. Whatever you provide gets converted to some form or the other. Now, all the energy cannot go to the charge carriers. Some of the energy is absorbed by the ions also, some of the energy is absorbed by neutral atoms also. But these atoms or ions being heavy to move, they do not move, they do not produce transport. Okay. So, they dissipate this extra energy via vibrations inside the lattice structure. These vibrating atoms inside a lattice are basically what is known as phonons. And when an electron hits these vibrating atoms or phonons, it gets scattered, and this mechanism is known as phonon scattering. And since these phonons are a part of the lattice structure, crystal lattice, you can also call this mechanism as a lattice scattering mechanism. Okay. So, scattering by these lattice waves, we say waves because when they are vibrating, they are producing sort of a wavy structure inside the 3-dimensional. A crystal is purely 3-dimensional arrangement. So, when these 3-dimensional arrangement of atoms start to vibrate, there is, you can call it a lattice wave. When this wave scatters your charge carriers, it can produce, it can include both absorption or emission of either acoustical or optical phonons. Okay. Acoustical basically means via heat or those kind of things, or optical phonons means when this energy get dissipated via light. Okay. But the basic mechanism is that your phonons are causing an effect on the mobility. These phonons represent nothing but a quanta of mechanical waves that travels throughout the semiconductor crystal. The density of phonons in a solid increases with temperature. So, the scattering time due to this mechanism will decrease with temperature, as will the mobility. Okay. So, when temperature increases, especially at high temperatures, your phonon scattering is also going to be very high, because you have applied higher energy. Not all energy can go to charge carriers. Okay. So, in that case, this extra energy goes to these phonons, via these phonons get dissipated, and this enhances the scattering of charge carriers at high temperature. So, at high temperatures, mobility can reduce because of phonon or lattice scattering. Okay. Lattice scattering is related to thermal motion of atoms. The rate at which the scattering occurs, as I have said, is a function of temperature. It dominates at high temperature and causes a reduction in mobility. If say in a semiconductor only phonon scattering is present, there is no other mechanism by which your charge carriers can get scattered. So, if only phonon scattering is present, your mobility is going to vary at T to the power minus 3/2, where T is temperature. Okay. So, at high temperature you are going to undergo a degradation in mobility. Okay. This scattering of mobility increases with temperature. Okay. Or you can also say that if you reduce the temperature, mobility increases. Okay. Apart from phonon scattering, you also have impurity scattering. Impurity, which basically means doping. When you do doping in an intrinsic semiconductor, you add impurity atoms which get converted to ions, either donor or acceptor ions. Again, these ions are heavy, so they do not move, but they can scatter your charge carriers. A positive donor ion can attract electrons, a negative acceptor ion can attract holes, a positive donor atom can repel some of the minority holes, same for electrons. Okay. So, the amount of scattering due to this electrostatic force between the charge carriers, electrons or holes, and the ionized impurities. Okay. So, in this say in an n type semiconductor, you have large number of negative electrons and you have positive donor ions. So, they have an electrostatic attraction. Same for p type semiconductor, you have lot of positive holes, but lot of negative acceptor ions. So, there is lot of electrostatic force. This kind of electrostatic interaction produces scattering of charge carriers. If you have lot of impurity, lot of dopant atoms, this scattering is going to increase. Okay. So, if temperature increases, the random thermal velocity of a carrier increases, reducing the time the carrier spends in the vicinity of these kind of ionized donors or acceptors. The less time spent basically means less attraction, Coulombic force, and smaller the scattering effect and larger the mobility. This basically means that this impurity scattering mechanism actually gets enhanced by or gets reduced by increase in temperature, because of which the mobility actually increases with the temperature if only impurity scattering was present. So, if in a semiconductor only impurity scattering was present, no other scattering mechanism existed, in that case your mobility is going to increase with temperature. Okay. So, overall effect is The effective mobility inside a semiconductor depends upon both mobility due to lattice or phonon scattering and mobility due to impurity scattering. Okay. Phonon or lattice scattering dominates at higher temperature and reduces your mobility. Okay. Similarly, at lower temperature mobility rises because of the reduced effect of impurity scattering. Okay. And this is the graph which basically tells you that when temperature increases, okay, mobility initially goes up due to impurity scattering and then it comes down due to phonon scattering. Okay. So, here your impurity scattering dominates, here lattice scattering dominates, and when you increase the doping, when doping concentration goes up, for very high levels of moderate to high levels of doping, mobility remains largely constant, but at extremely high levels of doping, because of lot of impurity ions around the charge carriers, lot of scattering takes place and your mobility starts to reduce, but this happens only at very high levels of doping. Okay. So, this is the effect of temperature and doping on mobility, right. Let us proceed further and we want to discuss the second mechanism of charge carrier transport, which is diffusion. Okay. So, we have done drift, we have done mobility, now we want to study the diffusion. This is the process by which particles flow from a region of higher concentration to a region of lower concentration. Okay. So, flow of carriers from one region which is higher concentration to another region which is lower concentration produces what is known as diffusion current. The gradient is always negative, because the region from which charge carriers are moving has higher concentration and to the region where they are moving has lower concentration. So, final minus initial in terms of concentration is always negative. Okay. So, the gradient of concentration is always going to be negative. Okay. So, you can see whenever holes diffuse, the whole diffusion current is in the same direction, but whenever electrons diffuse, the electron diffusion current is in the opposite direction. Okay. Because the movement of holes and hole current is same, but the movement of electrons and electron current produced by electrons is always opposite, right. So, this has to be kept in mind, the direction. The whole diffusion current is in the same direction in which the holes diffuse. Electron diffusion current is in the direction opposite to in which electrons are actually diffusing. Okay. So, hole diffusion current is in the direction of concentration gradient, electron diffusion current is in the direction opposite to this gradient. Okay. The diffusion current for electrons can be expressed as, so now as we said that the diffusion current by itself is dependent on what? It is dependent on concentration gradient. So, if you have a region, even if the region is localized in a very large semiconductor, there is a small localized region where there is a concentration gradient existing. Okay. In that region you can have diffusion current. Okay. So, a concentration gradient first has to exist for diffusion current to flow. So, this diffusion current is proportional to the charge as well as the concentration gradient. Okay. Now, you see that there are two negative signs here. This negative sign is because electron charge is negative. Okay. So, electrons have negative charge, there is one minus sign here. Second negative sign here is because I have said that the concentration gradient is always negative. Okay. So, if you have a region here with respect to distance, you have electron concentration, you have high, low and lower concentration. So, if you see this slope here, this slope of carrier concentration, this slope is negative. Okay. This dN by dx is a negative number. Because of this negative concentration gradient, there is another minus sign here. So, your net electron diffusion current is proportional to the product of q as well as dN over dx. Okay. So, diffusion current for electrons will do for holes also. For electrons it is proportional to q charge as well as the concentration gradient, the product, and the proportionality constant here is represented by d subscript n, where dN is known as the diffusion coefficient for electrons and the units are centimeter square per second. Okay. So, this is the this equation here tells you the electron diffusion current. Okay. Now, for holes again the same analogy applies, except a small difference. Now, hole diffusion current is also proportional to charge as well as concentration gradient, but the charge of holes is actually positive. Holes have a positive charge, okay, same as electron, but opposite polarity, okay, and the concentration gradient is negative. Okay. So, if I plot the hole concentration with respect to distance, holes are going to move from a region of higher concentration to a region of lower concentration. Okay. This slope which you are seeing here dP over dx is always negative. Okay. So, always remember, whenever we are talking about diffusion currents, we want a concentration gradient, and this gradient is always negative. Okay. But the charge here is positive. So, eventually your hole diffusion current is equal to minus sign q dP by dx, and the constant of proportionality is given as dP, which is known as diffusion coefficient for holes. Units are same, centimeter square per second. Okay. So, this equation in the middle basically tells you the hole diffusion current. Okay. So, now we have an expression for electron diffusion current as well as we have an expression for hole diffusion current. Okay. The total diffusion current in any semiconductor, we have already seen that it is because of both drift as well as diffusion. Okay. The total diffusion current can be because of electrons as well as holes, given by these equation which we have just seen. Okay. And overall inside a semiconductor, the total current has both drift as well as diffusion current. Drift can be because of both electrons and holes, diffusion can be because of both electrons and holes. Okay. So, this equation, this last equation is quite important for any semiconductor device. It basically gives you all the individual components of current which are present inside a semiconductor. So, you have an electron drift current, you have hole drift current, electron diffusion current and hole diffusion current. Okay. So, both drift and diffusion because of electrons as well as holes. This is the total current inside a current density inside a semiconductor. Okay. So, once we have the current components, let us see a very important relation which is generally applicable whenever there is diffusion current. Okay. It is known as Einstein relation. It relates two very major parameters. It relates the diffusion coefficient with the carrier mobility. Okay. So, both are very important parameters. Diffusion current, as we know, is because of a negative concentration gradient. After diffusion has happened for some time, okay, see what will happen. Say if you have a region, there are lot of electrons here, okay, there are lot of electrons here and there are very few electrons here. Okay. If I draw a cross section across this semiconductor, I can say let us call this region 1 and call this as region 2. Electrons are going to diffuse from a region of higher to lower concentration here, from here to here. After some time, this region is going to lose electrons, this region is going to gain electrons. Okay. The region which loses electrons develops small positive charge, the region that gains electrons develops some negative charge. Okay. So, I have generated some potential difference inside this material. Because of diffusion, a small potential difference is rising. Region which lost negative charge gained some positive charge, okay, because it lost electron. The region which received these electrons gained a small negative charge. Okay. So, this induces a net potential difference which is nothing but an electric field. Now, this electric field has not been applied, but it is induced. It is an intrinsic electric field which has been induced. Okay. The direction of this electric field is going to from here to here, positive to negative. which means an electron drift current can flow in this direction, but an electron diffusion current was flowing in the opposite direction. The diffusing direction and the diffusion current for electron is opposite. So, electron diffusion current is in this direction and the drift current is in this direction. So, they both oppose each other. So, the drift as well as diffusion current is going to cancel each other, right, and we know that drift current for electron is given by this equation and drift current diffusion current is given by this equation. Okay. So, diffusion tends to produce drift also, right. So, if drift is balancing this diffusion, electric field is created by this carrier concentration gradient, or it can have non-uniform doping also. Okay. The electric field by definition you can say that it is equal to energy gradient per unit charge. Okay. E c here represents your conduction band energy, okay. Because why we are taking this conduction band energy, see this region here, there going to be a higher probability of finding electron as compared with here. So, your energy band diagram is going to have a slope, okay. Whereas, the Fermi level remains constant at equilibrium, but other levels like E c, E v and E f I intrinsic Fermi level, they are going to have a gradient, right. So, your conduction band energy level, valence band energy level and the intrinsic Fermi energy level, they are going to have a certain slope like this. Okay. So, if this is E c, right, and this can be your E f, okay, and this can be E f I and this can be E v. Okay. So, here this is your region 1 and this is your region 3. You have lot of electrons here and you have less electrons here. So, E f is closer to E c here, E f is farther away from E c here. Okay. Since electron concentration is given by this expression here, from this equation if I differentiate with respect to x, okay, with respect to x if I differentiate, I am going to get this equation here. This term here is nothing but n again. So, dn by dx, the first order derivative of carrier concentration with respect to x. Okay. Now, we are talking about x, the distance, because the concentration gradient occurs in the spatial region with respect to x. So, region 1 had higher electron concentration, region 3 had lower electron concentration. Okay. This dn by dx is equal to minus q times E by kT by n. Why? If you see here, this when you differentiate, right, this is only going to give you d E c by dx, because E f is constant. Right. When you differentiate this term here, you are going to get n c exponential of minus of E c minus E f by kT, and when you differentiate this here, you are going to get minus d by dx E c minus E f by kT. Now, Fermi level is constant with respect to x. So, d E f by kT is going to be 0, but E c varies with respect to x. So, you are going to get d E c by dx, which is nothing but q times E. Okay. So, finally, you are going to get this expression here. This dn by dx I am going to substitute in this term here. Okay. So, this dn by dx is going to be substituted here. After substitution, right. So, after substitution, if dn by dx is equal to this, if I substitute this here, I am going to get this relationship, okay, because some of the terms are going to, E is going to cancel, N is going to cancel, okay, Q is going to cancel, right. So, eventually I get this relation where I say that d by mu is equal to kT by q. Now, this is for electrons. You can do the same thing for holes, except that you are going to have one minus sign here and one plus sign here, right. So, eventually the relation is going to be same. You are going to have a gradient in the energy band diagram for a p type semiconductor also. Okay. This relation which we have obtained, which says d by mu equal to k T by q. What is d? Diffusion coefficient. What is mu? Mobility. K is Boltzmann constant, T is temperature, q is charge. Okay. This k T by q, is also known as V T or thermal voltage. Okay. Why? Because K is constant, Q is constant. If you vary temperature, this term which has units of volts actually depends only on temperature. So, this is known as thermal voltage. So, d by mu is constant if temperature is constant, and this relationship is known as Einstein relation and is valid for both electrons as well as holes, valid for both n type and p type semiconductors. You can also relate d with what is known as diffusion length. Diffusion length is the amount of distance travelled by charge carriers before they basically annihilate. Before an electron falls into a hole, how much distance it travels is the diffusion length, and tau here is basically the lifetime. Okay. This time here is the lifetime of charge carriers. Okay. So, diffusion coefficient also helps you in calculating the diffusion length, how much distance a charge carrier travels while diffusing. Okay. So, with this these are some of the references you can refer to for this lecture. So, we end today's lecture. We have completed another useful topic, one related to mobility, another related to diffusion of charge carriers in a semiconductor device. So, we have done both drift as well as diffusion current and obtained an expression for Einstein relation. Thank you.